What if everything you've ever known, every star in the sky, every atom in your body, even the fabric of time itself, wasn't just part of the universe, but something far more extraordinary? Picture this: the entire cosmos, from the tiniest grain of sand to the vastest galaxy, might not be expanding outward into nothingness, but instead nestled within the heart of a black hole. It sounds like the plot of a wild sci-fi novel, but this is no fantasy. Some of the brightest minds in physics are asking a question that flips our understanding of reality on its head. Could we be living inside a black hole? Think about that for a moment. Black holes, those cosmic vacuum cleaners of the universe, known for crushing matter into oblivion, might not just be destroyers, they could be creators. The idea that our universe was born from the remnants of a collapsed star in another reality, or that the singularity at a black hole's core might be the seed of an entirely new existence, is as humbling as it is thrilling. This isn't just about rewriting textbooks, it's about reimagining our place in the grand scheme of things. If true, it would mean that every law of physics, every constant we take for granted, might be the unique signature of this hidden cosmic womb we call home. So how did this radical idea even come to be? And what clues in the universe hint that we might be living in the belly of a gravitational beast? Over the next few minutes, we'll trace the origins of this theory back to the edges of theoretical physics, where the rules bend and the impossible starts to feel plausible. We'll meet the scientists daring to ask these questions, explore the eerie parallels between black holes and the Big Bang, and uncover what it could mean if the universe we see is just one layer of a much deeper, stranger reality. By the end, you might never look at the night sky or your own existence the same way again. The journey starts now. The roots of this mind-bending theory stretch back to a time when disco ruled the airwaves and physicists were wrestling with some of the universe's biggest puzzles. In the early 1970s, a brilliant physicist named Nicodum Poplowski dared to ask a question that sounded more like science fiction than serious cosmology. What if the Big Bang wasn't the beginning of everything, but rather a rebirth, a cosmic phoenix rising from the ashes of a collapsed star in another universe? His radical idea suggested that when a massive star collapses into a black hole, the crushing forces at its core might not lead to destruction, but to creation. Instead of ending in a singularity of infinite density, the collapse could trigger the birth of an entirely new universe, hidden safely within the black hole's event horizon. This wasn't just a wild guess. Poplowski's work tapped into deep connections between Einstein's theory of general relativity and the strange rules of quantum mechanics. One of the most compelling pieces of the puzzle, the eerie similarities between the equations describing black holes and those explaining the expansion of our own universe. In both cases, matter and energy are compressed to extremes, space-time bends in ways that defy intuition, and the laws of physics as we know them start to unravel. It's almost as if the universe itself is hinting that black holes and cosmic births might be two sides of the same coin. But why would this theory matter beyond rewriting our cosmic origin story? For one, it could solve mysteries that have baffled scientists for decades. Take dark matter, the invisible glue holding galaxies together, or dark energy, the mysterious force accelerating the universe's expansion. If our universe was forged in the heart of a black hole, these phenomena might not be exotic substances at all. They could simply be echoes of the parent universe's physics, imprinted on our own. Imagine inheriting traits from a cosmic ancestor, like the way your eyes might mirror your grandmother's. Only in this case, the inheritance isn't genetic, it's woven into the fabric of space itself. Of course, not every scientist is convinced. Skeptics point out that while the math is elegant, we still lack direct evidence to prove we're living inside a black hole. But here's where things get even more intriguing. Some researchers suggest that if this theory is true, there might be subtle fingerprints hidden in the cosmic microwave background, the afterglow of the Big Bang, or in the way gravity behaves at the largest scales. Finding those clues would be like discovering a message in a bottle, washed ashore from a reality we can't even begin to imagine. Until then, the black hole universe theory remains one of the most daring and poetic ideas in modern physics, a reminder that sometimes the truth is stranger than anything we could invent. Black holes have long been painted as the ultimate villains of the cosmos, unstoppable monsters that devour everything in their path. But what if we've been looking at them all wrong? Instead of cosmic wrecking balls, they might actually be the universe's most astonishing midwives. Picture this: at the very moment matter gets crushed beyond recognition inside a black hole's singularity, the unimaginable pressure might not lead to oblivion but to rebirth. In the extreme environment where gravity warps space and time into knots, the rules of physics as we know them break down, and something extraordinary could take their place. This idea hinges on a concept called quantum bounce. When a dying star collapses into a black hole, most theories suggest it forms a point of infinite density, a singularity where all bets are off. But some physicists propose that quantum effects, the same strange rules governing particles at microscopic scales, could prevent total collapse. Instead of reaching infinity, the matter might rebound like a spring compressed to its limit, triggering an explosive expansion. Sound familiar? It's eerily similar to what we think happened during the Big Bang. In this scenario, every black hole could be a cosmic nesting doll, harboring an entire new universe within its depths, one with its own laws of physics, its own stars, and perhaps even its own black holes birthing yet more realities. Here's where it gets even wilder. If our universe was born this way, it would explain some of cosmology's biggest head-scratchers. Why does our universe seem so finely tuned for life? If we're the product of a black hole in a parent universe, our physical constants might simply be inherited like genetic traits passed down through generations. Even the mysterious dark energy accelerating the expansion of our cosmos could be a relic of that primordial bounce. And if black holes are birthing new universes, it raises a spine-tingling possibility. Our own universe might contain black holes that are, right now, spawning their own cosmic offspring. We could be living in just one link of an endless chain of universes, each inside the other like layers of an infinite onion. Of course, the biggest question remains: how could we ever prove this? Some scientists are looking for subtle distortions in the cosmic microwave background, the faint afterglow of the Big Bang, that might bear the fingerprints of a parent universe's black hole. Others suggest that the peculiar way galaxies rotate, or the uneven distribution of matter in the cosmos, could hold clues. Until we find definitive evidence, the idea remains a dazzling hypothesis, one that turns black holes from cosmic boogeymen into something far more profound. They might not just be the end of stars, but the beginning of everything. The holographic principle takes this cosmic mystery to an even more bewildering level, one where the very fabric of our three-dimensional reality might be nothing more than an illusion. Imagine your entire existence, every touch, every sunset, every galaxy swirling in the void, not as solid, tangible things, but as a grand projection, like shadows dancing on the wall of a cave. This idea, emerging from the depths of string theory, proposes that all the information encoding our universe could actually be stored on a two-dimensional surface, the event horizon of a black hole. It's as if everything we see and experience is just a hologram, a cosmic movie screen playing out the illusion of depth. At the heart of this theory lies a strange paradox about black holes. When matter falls into one, it doesn't just vanish. It leaves an imprint on the black hole's event horizon, the point of no return. This imprint isn't just a crude smear. It's a precise, information-rich pattern, like a barcode etched into the fabric of space-time. The holographic principle takes this a step further, suggesting that what we perceive as our universe might simply be the decoded version of that information, projected inward like light through a film reel. In other words, the stars, planets, and even your thoughts could be nothing more than echoes of data written on the surface of a black hole we can never see. This raises a dizzying question. If we're just holographic projections, what does that mean for space and time as we know them? Suddenly, the rigid laws of physics start to feel more like lines of code in a vast cosmic program. Distance, duration, even causality, the very foundations of reality, might be emergent properties, not fundamental truths. Think of it like a video game. The world you explore on screen feels real, with mountains, oceans, and weather systems, but underneath, it's all just ones and zeros. If the holographic principle is correct, our universe operates the same way. The real stuff isn't the 3D world we inhabit, but the 2D data scribbled on the edge of a black hole we'll never reach. But how could we possibly test such an outlandish idea? Some physicists are looking for telltale pixelation in the fabric of space-time, a tiny, imperceptible graininess that would betray the universe's holographic nature, like spotting the individual dots on a newspaper photo if you looked close enough. Others suggest that anomalies in the cosmic microwave background, the faint glow left over from the Big Bang, might hold encoded patterns pointing to a deeper, two-dimensional reality. Even gravity itself could be a clue. In a holographic universe, gravity might not be a fundamental force, but a side effect of the way information is projected into our three-dimensional illusion. Whether this theory holds up or not, it forces us to confront a humbling possibility that everything we consider real might be nothing more than a shadow on the wall of something far stranger. The holographic principle doesn't just challenge our understanding of black holes, it turns the nature of existence itself into an open question. And if it's true, then the greatest mystery isn't just whether we live inside a black hole, but whether we're even living at all, or just reading the lines of a script written on the edge of the abyss. If our universe truly is nestled inside a black hole, then the walls of our cosmic home might be thinner than we ever imagined, not just separating us from empty space, but from countless other universes, each with its own laws of physics, its own stars, and perhaps even its own thinking beings gazing up at their own version of the night sky. This isn't just wild speculation, it's a direct consequence of the black hole cosmology theory. Picture a cosmic Matryoshka doll, where every black hole in our universe could contain an entire new cosmos, and every one of those universes might harbor black holes of its own, spawning yet more realities in an endless mind-bending chain. The multiverse theory, once confined to the fringes of physics, takes on a startling new form when viewed through this lens. Instead of parallel universes existing side by side in some vast, abstract higher-dimensional space, they could be stacked inside one another, hidden behind event horizons like rooms in an infinite cosmic hotel. And here's where it gets even stranger. Some researchers suggest that these nested universes might not be entirely cut off from one another. Just as sound waves can travel through walls, gravitational waves, ripples in the fabric of space-time, might carry faint echoes from these sibling realities. Imagine listening to the cosmos and hearing not just the collisions of black holes in our own universe, but the distant murmurs of titanic events happening in realities beyond our own. But how could we possibly detect such echoes? The key might lie in the peculiar way gravitational waves behave when they're born near the edge of a black hole's event horizon. In a normal universe, these waves spread out and fade as they travel. But if our universe is inside a black hole, the geometry of space-time could act like a hall of mirrors, bending and reflecting gravitational waves in ways that leave subtle fingerprints. Some physicists are already scouring data from observatories like LIGO and Virgo, searching for anomalies, repeats, delays, or distortions in gravitational wave signals that might hint at something far grander than a simple collision. Finding even a single unexplained echo could be the first clue that we're not just hearing the universe, but listening in on the cosmic conversation of a multiverse. Of course, not everyone is convinced. Critics argue that these echoes could just as easily be noise in the data or artifacts of our imperfect detectors. But the tantalizing possibility remains. If we're living in a black hole, then every gravitational wave detection might be more than a scientific breakthrough. It could be a message in a bottle, sent from a reality we can never visit but might one day learn to understand. And if that's true, then the universe isn't just stranger than we imagine. It's stranger than we can imagine, with layers upon layers of mystery waiting to be unraveled. One of the strangest consequences of living inside a black hole would be the way time itself unravels. Picture standing at the edge of a waterfall, watching the water plunge into the abyss below. From your vantage point, the flow seems steady, predictable, but if you could peer over the edge, you'd see the water slow to a crawl as gravity warps its descent. That's precisely what happens to time near a black hole's event horizon. To an outside observer, clocks near the edge appear to tick infinitely slow, as if frozen in place. But here's the twist. If we're inside that black hole, our experience would be completely different. For us, time would feel normal, steady, linear, just as it does right now. This bizarre phenomenon comes straight from Einstein's theory of relativity, which tells us that time isn't some universal metronome ticking at the same rate everywhere. It's flexible, stretching and compressing depending on gravity's grip. Near a black hole where gravity is unimaginably strong, time distorts so severely that from the outside, our entire universe might appear frozen in a single moment like a cosmic still frame. Yet within our reality, life unfolds second by second, year by year, with no hint of the grand illusion. It's as if we're characters in a movie, unaware that the projector could pause at any moment. But what if this time warp goes even deeper? Some physicists speculate that if our universe resides within a black hole, the Big Bang itself might not have been a beginning, but a transformation, a moment when time, as we know it, switched dimensions. Imagine a river flowing toward a whirlpool. From afar, the water seems to vanish into the vortex, but beneath the surface, it might emerge somewhere else, redirected into a new current. In the same way, the arrow of time in our universe could be a continuation of something older, repurposed from the physics of a parent cosmos we'll never see. This raises a haunting possibility. Our perception of time's flow might be nothing more than a side effect of where we're standing in the cosmic maze. Just as a fish doesn't notice the water it swims in, we might be oblivious to the true nature of time because it's the only version we've ever known. The past, present, and future could be illusions, artifacts of a deeper structure we're only beginning to glimpse. Even more unsettling, if time is this malleable, then free will, our sense of making choices in a linear timeline, might be as fragile as a shadow cast by flickering light. Yet there's hope for unraveling the mystery. Scientists are already studying extreme gravitational environments, like colliding black holes, to see how time behaves under conditions that push relativity to its limits. Subtle anomalies in gravitational wave data or quirks in the cosmic microwave background might one day reveal whether our timeline is truly linear or just a local projection of something far more complex. Until then, the question lingers, is time the river we're sailing, or just the reflection of a deeper, darker current? Dark matter and dark energy, those shadowy giants of the cosmos, have long been the most stubborn puzzles in modern physics. Together, they make up 95% of everything in the universe, yet we can't see them, touch them, or even fully explain them. But what if these enigmatic forces aren't just features of our universe? What if they're cosmic fingerprints left behind by the reality that birthed us? If we're truly living inside a black hole, dark matter and dark energy might not be standalone mysteries at all. They could be echoes of the parent universe's gravity bleeding through the walls of our cosmic prison. Take dark matter first. We know it's there because galaxies spin faster than they should, held together by invisible glue we can't detect. But if our universe is nestled within a black hole, that extra gravity might not be coming from some exotic particle. It could be the gravitational shadow of the outer universe, stretching into ours like a hand pressing against a curtain. Think of it like hearing muffled music through a wall. You can't see the source, but you know it's there. In this case, the music is the gravity of stars, planets, and black holes from the parent cosmos, warping our space-time in ways we mistake for dark matter. Then there's dark energy, the mysterious force accelerating the expansion of our universe. If we're inside a black hole, this acceleration might not be driven by some unknown energy at all. It could be the pressure of the outer universe pushing inward. Picture a balloon inflating inside another balloon. As the outer one contracts, it squeezes ours, making it expand faster. In this scenario, dark energy isn't a thing but an effect, a cosmic illusion created by the gravitational tension between our universe and the one that contains it. This idea isn't just poetic, it's mathematically plausible. Some models suggest that the equations describing black hole physics and cosmic expansion align eerily well when you account for leakage from a parent universe. Even the rate of our universe's expansion, which seems finely tuned to allow life to exist, might simply be a consequence of this nesting. It's like inheriting the rhythm of your heartbeat from your mother's biology. No divine fine-tuning required, just the natural physics of cosmic ancestry. Of course, the challenge is proving it. If dark matter and dark energy are really gravitational artifacts from beyond our event horizon, their signatures should be subtly different from what traditional models predict. Some physicists are searching for anomalies in the way galaxies cluster or how light bends across the cosmos, hunting for distortions that might betray the presence of an outside influence. Others are re-examining the cosmic microwave background, looking for patterns that resemble the imprint of a parent universe's structure. Until we find definitive evidence, this remains one of the most tantalizing what-ifs in cosmology. But if it's true, it would mean that the darkest parts of our universe aren't just empty mysteries, they're messages, whispers from a reality we can never see but might one day learn to read. And that changes everything. Quantum entanglement is one of the most baffling phenomena in physics. Particles separated by light years can instantaneously influence each other, as if they're dancing to some hidden, universal rhythm. Now imagine this eerie connection isn't just a quirk of our universe, but a cosmic thread tying us to the reality that birthed ours. If we're truly living inside a black hole, entanglement might not be a random feature of quantum mechanics. It could be a relic, a faint whisper of information carried over from the parent universe that collapsed to form our own. This idea takes the black hole information paradox, a decades-old debate about whether information swallowed by a black hole is destroyed or preserved, and flips it on its head. Normally, we think of black holes as cosmic shredders, obliterating everything that falls in. But quantum mechanics insists information can't truly vanish. It might be scrambled, hidden, or transformed, but never erased. So where does it go? If our universe is the offspring of a black hole, that lost information might not be lost at all. Instead, it could be woven into the fabric of our reality, encoded in the entangled particles that make up everything from starlight to your own DNA. Picture it like this: when a star collapses into a black hole in some distant ancestral universe, its final moments aren't erased, they're imprinted onto the event horizon, a process physicist Stephen Hawking called Hawking radiation. But instead of radiating away into nothingness, that information might get folded into the new universe born from the collapse. The entangled particles we observe today could be the unraveled strands of that original data, like pages from a book scattered by a cosmic explosion but still faintly legible. This would mean the quantum links we see aren't just random. They're echoes of a deeper connection, a hidden ledger keeping track of everything that came before. Even the apparent randomness of quantum events, where particles seem to choose their states on a whim, might not be chaos at all. It could be the faint, distorted reflection of processes happening in a reality we'll never see, like shadows cast by a fire burning in another room. The implications are staggering. If entanglement is a bridge to a parent universe, then every experiment probing quantum mechanics might unknowingly be sifting through cosmic archaeology, uncovering fragments of a lost world. Some researchers even suggest that certain patterns in the cosmic microwave background, the afterglow of the Big Bang, could contain encoded signatures of that primordial information, like a message in a bottle washed ashore from a forgotten ocean. Of course, not everyone agrees. Skeptics argue that without a way to directly observe this proposed connection, it's little more than a beautiful metaphor. But supporters counter that the very existence of quantum entanglement, a phenomenon with no intuitive explanation in our universe, might be the clue we've overlooked. After all, if information truly can't be destroyed, then the answers we're seeking might not be lost. They could be hiding in plain sight, written into the fabric of reality itself, waiting for us to learn how to read them. Whether this theory holds up or not, it forces us to confront a profound possibility: that the mysteries of quantum mechanics aren't just puzzles to solve, but breadcrumbs leading us back to our cosmic origins. Every entangled particle, every flicker of uncertainty in the quantum realm might be a piece of a much larger story, one that began not with our Big Bang, but with the death throes of another universe entirely. And if that's true, then the universe isn't just stranger than we imagine. It's a living testament to the unbreakable bonds that tie all of existence together. The Big Bang has always been portrayed as the ultimate beginning, a fiery explosion from nothingness that birthed space, time, and everything we know. But what if that iconic moment wasn't a true beginning at all? What if it was just a turning point in an endless cosmic cycle, like the moment a phoenix rises from its own ashes? This is where the black hole universe theory takes one of its most daring leaps. The idea that the Big Bang wasn't a singular creation event, but the rebound of a singularity from another universe's collapsed black hole. Think of it like this: when a massive star dies, it doesn't just fade away. It implodes with such force that it punches a hole in space-time, creating a black hole. At the very center of that black hole lies the singularity, a point where gravity becomes infinite and the laws of physics break down. Most theories assume this is the end of the story, a one-way trip to oblivion. But what if, under conditions we don't yet understand, that singularity doesn't just vanish? What if it rebounds like a compressed spring snapping back, triggering an explosion of energy and matter so vast it births an entirely new universe? This isn't just poetic speculation. The math behind Einstein's general relativity allows for such a scenario, and some quantum gravity models even suggest it might be inevitable. In this view, the Big Bang's infinitely dense point wasn't a mysterious starting line. It was the dying breath of a previous cosmos, recycled into something new. The expansion we see today, the galaxies racing away from each other, might not be the aftermath of creation but the echo of a far older collapse. The implications are staggering. If true, it means our universe isn't the first and only iteration of reality. It's just the latest chapter in an endless story. Each time a black hole forms in some parent universe, it could spawn a child universe with its own unique physics, like a cosmic game of telephone where the rules subtly change with each retelling. Our finely tuned constants, the strength of gravity, the mass of an electron, might not be carefully designed at all. They could just be inherited traits, random rolls of the dice from a long line of cosmic ancestors. This also solves one of the most perplexing riddles in cosmology. What came before the Big Bang? If our universe was born from a black hole, then before wasn't empty nothingness. It was another universe with its own stars, planets, and perhaps even life, now lost behind the event horizon of oblivion. We're not the first, we're just the latest, and if black holes in our own universe are spawning new realities, then the cycle continues, an infinite cascade of creation and destruction stretching forever in both directions. But how could we ever prove such a thing? Some researchers suggest looking for faint imprints in the cosmic microwave background anomalies that might carry the scars of a parent universe's structure, like a fossil pressed into clay. Others propose that the distribution of dark matter or the way black holes spin could hold clues, subtle hints of inheritance from a reality we'll never see. Until then, this remains one of the most humbling ideas in physics, that our entire existence might not be a singular miracle, but a single link in an unbreakable chain stretching back and forward further than we can possibly imagine. Proving we're living inside a black hole might sound like the plot of a sci-fi detective story, but scientists are dead serious about hunting for clues, and they're starting with the oldest light in the universe. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint whisper of radiation filling every corner of space. If our universe was born from a black hole's collapse, this primordial light should carry subtle fingerprints of that violent origin. Imagine examining a piece of pottery for cracks. The CMB is our cosmic relic, and its imperfections might reveal the shape of the kiln that forged it. Some theories predict that the CMB should show unusual patterns, circular imprints, or temperature asymmetries that align with the way a black hole's event horizon would distort spacetime during a universe's birth. It's like finding a watermark on a document, proof of its origin. Already, researchers have spotted odd anomalies in the CMB, like the axis of evil, a mysterious alignment of fluctuations that defies standard cosmology. Could these be echoes of a parent universe's gravitational pull, etched into our sky? Skeptics argue it's just cosmic noise, but if future telescopes like the James Webb or the upcoming LightBird mission detect more of these anomalies, the black hole hypothesis could move from fringe to forefront. Then there's the shape of the universe itself. According to Einstein's equations, a universe born from a black hole might not be perfectly flat or infinite. It could curve in ways that reflect its cramped beginnings. Picture a balloon inflating inside a box. Its surface would bear dents and warps from the container's walls. If our universe has a slight curvature or closed geometry, it might hint at the walls of our cosmic prison. Current measurements suggest the universe is flat, but the margin of error leaves room for surprises. Upgraded galaxy surveys, like those from the Euclid Space Telescope, could settle the debate by mapping the universe's structure with unprecedented precision. But the most tantalizing clues might come from the way galaxies are scattered across the cosmos. If we're inside a black hole, the distribution of matter could resemble the debris left after a whirlpool's collapse, clustered in ways that mirror the spin of the original singularity. Some models even suggest that black hole universes would inherit a preferred direction of rotation, leaving galaxies aligned like iron filings around a magnet. Astronomers are already studying galaxy rotations for odd symmetries, and while nothing definitive has emerged, the search is far from over. The James Webb Space Telescope could be a game changer. Its ability to peer back at the universe's first galaxies might reveal structures too perfectly aligned or clustered to be random. If ancient galaxies appear to, remember, a shared origin like fragments of a shattered mirror still reflecting the same light, it could point to a birth event more violent than the gentle Big Bang we've long imagined. Of course, absence of evidence isn't evidence of absence. Even if these searches come up empty, the black hole universe theory could adapt, proposing subtler signatures or rarer phenomena to chase. That's the beauty and frustration of cosmology. The answers are written in the sky, but decoding them takes patience, ingenuity, and a willingness to question everything we think we know. Whether the theory holds up or not, the hunt itself is reshaping our understanding of reality, one cosmic clue at a time. If our universe is truly nested inside a black hole, it doesn't just reshape our cosmic address, it rewrites the very meaning of existence. Suddenly, questions we've pondered for millennia take on startling new dimensions. Take free will, for instance. If every event in our reality is ultimately the offspring of a singular, deterministic collapse, a star's implosion in another universe, does that mean our choices are just dominoes falling in a chain reaction that began eons ago? Or could quantum uncertainty, those tiny gaps in predictability, be the cracks where genuine agency slips through? This isn't just theoretical musing. It's a collision between physics and philosophy, where the nature of consciousness itself might hinge on the architecture of our cosmic cradle. Then there's purpose. For centuries, humans have looked to the stars for meaning, wondering if we're part of some grand design. But if we're the byproduct of a black hole's rebirth, does that render us accidental or astonishingly inevitable? On one hand, the idea that our universe emerged from a random stellar collapse feels humbling, almost impersonal. Yet there's a counterargument that's strangely beautiful. In this scenario, black holes aren't just destroyers but creators, cosmic engines forging new realities with each collapse. We might not be the center of the universe, but we're proof of an extraordinary process, one where destruction and creation are two sides of the same coin. The blurring goes deeper when we consider reality itself. If the holographic principle holds, and our three-dimensional world is just a projection of data encoded on a black hole's event horizon, then what's truly real? The chair you're sitting on, the screen in front of you, are they tangible objects or merely the universe's way of interpreting information from a shadow realm we can't access? It's a modern twist on Plato's cave, where the shadows aren't illusions but the only reality we'll ever know. This doesn't diminish our experience, it reframes it. The warmth of sunlight, the taste of fruit, the sting of loss, they're no less vivid because they might be emergent phenomena. If anything, their fleeting nature becomes more precious. Perhaps the most profound implication is the challenge to our isolation. If black holes birth universes, then we're not just solitary wanderers in the void. We're part of an unimaginably vast family tree, linked to countless other realities through the gravitational wombs that birthed them. The laws of physics here might be unique, but they're not alone. They're variations on a theme, like dialects of a cosmic language. Even if we can never visit those sibling universes, their existence suggests a deeper order, a fractal pattern of existence stretching beyond our horizon. Ultimately, living in a black hole doesn't answer life's big questions. It makes them richer, more layered. Whether we're accidents or inevitabilities, illusions or projections, one thing becomes clear: the universe is far stranger and far more interconnected than we ever dared dream. And that realization isn't just science, it's the kind of awe that borders on reverence. The idea that our universe might be a holographic projection inside a black hole already stretches the limits of imagination. But what if it goes even further? What if this cosmic nesting doll isn't just a natural phenomenon, but something far more deliberate? Enter the simulation hypothesis, the provocative theory that our reality might not be a physical universe at all, but an intricately coded construct, a digital mirage crafted by some unfathomably advanced civilization. At first glance, it sounds like pure science fiction, but when you layer it over the black hole universe theory, the lines between physics and philosophy start to blur in startling ways. Think about how we already use simulations. Scientists model entire galaxies inside supercomputers, creating virtual worlds governed by adjustable rules. Now imagine a civilization millions of years ahead of us, with technology so advanced they could harness the very fabric of space-time. For them, creating a black hole might not just be an astronomical event, it could be the ultimate programming tool. A black hole singularity, with its infinite density and warped physics, might serve as the perfect processor, crunching data into an entire universe's worth of experience. In this scenario, our Big Bang wasn't a random rebound from a collapsed star. It was the boot-up sequence of a cosmic server humming with the code of our reality. This isn't just wild speculation. The holographic principle, which suggests our three-dimensional world is a projection of information stored on a two-dimensional surface, fits eerily well with how simulations operate. In a computer, every detail from the flight of a bird to the spin of an electron is ultimately reducible to bits, binary code etched onto a hard drive. If our universe is holographic, then the event horizon of our parent black hole could be that hard drive, with every particle and force in our existence just a rendering of deeper data. Even quantum indeterminacy, the randomness at the heart of particles, might not be true chaos, just the procedural generation of a universe-size algorithm, filling in the blanks as we observe them. But here's where it gets even more mind-bending. If black holes can birth universes, and if advanced civilizations could engineer them, then the simulation hypothesis isn't just about us being someone else's experiment. It suggests a fractal cascade of realities, each nested inside the other, like layers of an infinite cosmic onion. Our creators might themselves be simulations, living inside a black hole forged by another civilization, ad infinitum. It's a hall of mirrors with no original, no base reality, just an endless recursion of existence. Of course, skeptics push back hard. They argue that even if the math allows for such possibilities, there's no empirical evidence to suggest we're in a simulation, let alone one housed in a black hole. But proponents counter that the very laws of physics might be the clue. Why, for example, does the universe operate on mathematical rules at all? Why do particles follow predictable equations unless those equations are the underlying code? Even the speed of light, the universe's ultimate speed limit, could be seen as a processing constraint, the system lag of a cosmic computer. The debate forces us to confront an unsettling question: how would we ever know? Some scientists propose looking for glitches, in reality tiny inconsistencies in physical laws, or pixel-like patterns in the fabric of space-time. Others suggest that high-energy particle collisions might reveal the resolution of our universe, like zooming in on a digital image until you see the individual pixels. So far, no such smoking gun has emerged, but the search itself reveals something profound. Whether we're in a simulation or not, the universe is stranger than we ever imagined. Perhaps the most humbling takeaway is that these two ideas, black hole cosmology and the simulation hypothesis, aren't mutually exclusive. They could both be true or neither. But together, they remind us that reality, whatever it is, operates on levels deeper than our everyday experience can grasp. Whether we're stardust or lines of code, the wonder isn't just in the answers we might find, but in the fact that we're here at all, asking the questions. And that, in itself, is a kind of magic no simulation could ever replicate. Long before telescopes or quantum physics, ancient sages in India and Tibet spoke of universes breathing in and out endless cycles of creation and dissolution woven into the fabric of existence. The Hindu concept of pralaya, the cosmic night when all things return to the source, or Buddhism's kalpas, vast epochs where worlds rise and fall like waves, eerily foreshadow what modern equations now suggest, that black holes might be the engines of this eternal return, cosmic alchemists turning collapse into rebirth. Fast forward to the 20th century, where physicists like Richard Tolman and Roger Penrose began sketching a radical vision, one where the universe doesn't end in heat death or a big crunch, but folds back into a singularity, only to explode anew. The math reveals something astonishing. Under certain conditions, a collapsing black hole singularity might not be a dead end, but a cosmic reset button. Picture a rubber band stretched to its limit. The moment it snaps back isn't the end, but the beginning of another stretch. In this model, black holes aren't tombstones, they're turnstiles, recycling the raw materials of reality into fresh beginnings. The implications ripple outward. If each black hole spawns a new universe, then our own cosmos might be one of countless iterations, each with slightly tweaked physics. Some universes could be stillborn, collapsing instantly under their own rules, while others, like ours, stumble into the precise balance needed for stars, planets, and life. This isn't just about cosmic reincarnation, it's a potential answer to why our universe seems so finely tuned. There's no designer, no miracle, just trial and error across infinite cycles, with life emerging in the rare versions where the numbers align. Yet the most haunting question remains, could traces of past universes linger in ours? Some theorists suggest that gravitational waves, those ripples in space-time from colliding black holes, might carry faint imprints of earlier cycles, like echoes in a cave growing fainter with each rebound. Others hunt for anomalies in the cosmic microwave background, patterns that don't fit the standard Big Bang narrative but might whisper of a universe that came before. Even the mysterious dark flow, where clusters of galaxies drift en masse toward an unseen attractor, could hint at gravitational scars from a parent cosmos. Of course, not all scientists are convinced. Critics argue that without observable proof, cyclic models are more philosophy than physics. But supporters counter that absence of evidence isn't evidence of absence after all. Black holes were once dismissed as mathematical fantasies until we found them peppering the sky. Whether the cycles are real or not, the poetry is undeniable. In this vision, death isn't an end but a transformation, and every black hole a potential cradle for realities yet unborn. The universe, it seems, has always known how to turn endings into beginnings. We're just beginning to catch up. White holes are the cosmic opposites of black holes, not cosmic vacuum cleaners, but cosmic fire hoses, violently ejecting matter and energy instead of swallowing them. While black holes trap everything behind an event horizon, white holes push everything outward, refusing to let anything back in. These hypothetical objects have never been observed, but they emerge naturally from the same equations that predict black holes, like shadows cast by the mathematics of relativity. And if they exist, they could rewrite our origin story in the most dramatic way possible. Imagine a black hole in some distant, ancient universe collapsing in on itself. According to standard physics, that collapse leads to a singularity, a point of infinite density where the laws of physics break down. But what if, on the other side of that singularity, the matter doesn't just vanish? What if it rebounds, erupting into a new space-time like a geyser bursting from the ground? That eruption would be a white hole, a big bang in its own right. In this scenario, our universe isn't just inside a black hole. It's the explosive output of a white hole, the other side of a cosmic coin. We wouldn't just be living in the aftermath of a collapse, we'd be the debris flung outward from a reality that no longer exists. This idea flips our understanding of time on its head. In the parent universe, the black hole's formation is a one-way trip to oblivion, a final act of destruction. But from our perspective, that same event is the beginning of everything, a birth, not a death. It's as if time itself forks at the singularity, with one universe's end becoming another's genesis. This could explain why our universe appears to have a clear starting point, the Big Bang, while the parent universe's timeline remains forever hidden behind an event horizon we can never cross. The implications ripple outward. If our universe is a white hole's eruption, then the structure of space-time might still carry scars from that violent birth. Some physicists speculate that anomalies in the cosmic microwave background, the faint glow left over from the Big Bang, could reveal a preferred direction, a faint axis pointing back toward our point of origin. Others suggest that the distribution of galaxies, or even the nature of dark energy, might encode hints of our cosmic ancestry. If we're the exhaust of a black hole's collapse, then the universe isn't just expanding, it's still recoiling from the initial explosion, like a firework's embers drifting away from the blast. But the most tantalizing possibility is that white holes could be part of an endless cycle. If every black hole collapse spawns a white hole eruption, then universes might be chained together in an infinite sequence, each one's death becoming another's birth. Our cosmos could be one link in a vast, unbreakable chain, with black holes in our own universe already gestating new realities we'll never see. It's a vision both humbling and exhilarating. We're not just stardust, but the echoes of a process as old as time itself. Of course, skeptics argue that white holes remain purely theoretical, mathematical curiosities with no evidence to prove they exist. Without a way to observe them directly, the idea risks drifting into the realm of philosophy. But that's the beauty of cosmology. Sometimes the wildest ideas are the ones that push us to look harder, to dig deeper into the data for clues we might have missed. Whether white holes are real or not, the mere possibility forces us to rethink our place in the cosmos, not as the center of existence, but as a single note in an endless symphony of creation and destruction. And that, in itself, is a revelation worth exploring. Gravitational waves are like cosmic sonar ripples in the fabric of space-time that echo with the secrets of the universe's most violent events. When black holes collide or neutron stars spiral into each other, they send out these waves at the speed of light, carrying fingerprints of their cataclysmic origins. But if we're living inside a black hole, these waves might be more than just messengers from distant corners of our universe. They could be cosmic telegrams smuggled through the event horizon from the parent reality that birthed ours. Think of it like tapping on a prison wall. If you listen closely, the vibrations might carry hints of what's happening on the other side. In this case, the wall is the boundary of our black hole universe, and the taps are gravitational waves from collisions in the outer cosmos. Normally, these waves would fade into the background, indistinguishable from the noise of our own universe's events. But if the parent universe's gravity leaks through even faintly, it could distort the waves in subtle, telltale ways. Imagine hearing a song played through a thick door. The melody's still there, but the notes are warped, stretched, or echoed in ways that betray the barrier. Scientists are now training their instruments to listen for those very distortions. The key lies in the afterglow of collisions. When two black holes merge, they produce gravitational waves with a specific signature, a crescendo of ripples followed by a fading ring-down like a bell's final toll. But if our universe is nested inside another black hole, that ring-down might not fade cleanly. Instead, it could show faint repetitions or delays, as if the waves are bouncing off the hidden walls of our cosmic enclosure. Some researchers call these echoes, and while they're still controversial, a handful of gravitational wave detections by LIGO and Virgo have shown curious bumps in the data, tiny anomalies that don't fit standard models. Could these be the first whispers from beyond our event horizon? Even more tantalizing is the possibility of decoding these signals. If gravitational waves from the parent universe carry imprints of its physics, its constants, its structure, they could reveal whether our laws of nature are unique or just one variation in an infinite multiverse. It's like finding a letter washed ashore in a bottle. The words might be faded, but if you piece them together, they could tell you where the current came from. Some theories suggest that advanced civilizations in the parent universe might even manipulate black holes intentionally, using them as cosmic antennas to send information or warnings to offspring universes like ours. Of course, skepticism abounds. Many scientists argue that the alleged echoes could just be noise in the detectors or artifacts of imperfect data analysis. After all, gravitational wave astronomy is still in its infancy, and teasing faint signals from the cosmic static is like listening for a whisper in a hurricane. But the hunt is far from over. Upcoming upgrades to gravitational wave observatories like the space-based LISA mission will sharpen our ears to frequencies previously inaudible. If those whispers are real, we might soon have the tools to hear them clearly, and with them, the first clues to our true cosmic lineage. Until then, every gravitational wave detection is more than just a scientific milestone. It's a potential message in a bottle, cast adrift from a shore we can never visit but might one day learn to understand. And if we're right about their origin, then the universe isn't just speaking to us, it's telling us where we came from. The eerie silence of the cosmos has haunted scientists for decades, a paradox first posed by physicist Enrico Fermi when he asked, "Where is everybody?" If the universe is teeming with potential life, why haven't we found a single whisper of another civilization? But what if we've been searching in the wrong dimension altogether? If black holes truly birth universes, then advanced civilizations might not be broadcasting signals across the void. They could be thriving inside black holes, using these cosmic furnaces not as traps, but as gateways to new realities, places where the laws of physics might be more hospitable, or where resources are infinitely renewable. Consider this: a civilization mastering black hole technology wouldn't just exploit these objects for energy, they'd colonize them. Picture a society so advanced that dying stars aren't threats but opportunities. They could engineer controlled collapses, crafting bespoke universes tailored to their needs, like architects bending space-time to their will. In this scenario, the reason we don't see alien megastructures or hear interstellar radio chatter isn't because civilizations are rare. It's because they've graduated beyond our observable plane, retreating into layers of reality we can't yet access. The universe's silence isn't a sign of absence, it's a sign of evolution. This idea flips the Fermi paradox on its head. Instead of asking why we're alone, we might ask, What if we're just late to the party? If black hole universes are the cosmic equivalent of gated communities, then the most advanced beings wouldn't be broadcasting their presence. They'd be invisible by design, hidden behind event horizons as impenetrable as fortress walls. Even their energy consumption might leave no trace. A civilization harvesting a black hole's power from the inside would appear to us as nothing more than a quiet singularity. The cosmos isn't empty, it's a nesting doll of civilizations, each tucked safely inside its own pocket of space-time. But here's the twist, we might already have clues hiding in plain sight. Take fast radio bursts, those mysterious high-energy pulses from deep space. Some scientists speculate they could be artificial, perhaps even leakage from experiments in black hole engineering. Or consider the bizarre behavior of certain quasars, whose energy output defies conventional astrophysics. Could these be the exhaust fumes of civilizations tinkering with singularities? The answer might not lie in scanning the stars for radio waves, but in studying black holes for anomalies that betray intelligent manipulation. Of course, skeptics argue this is speculative at best, a cosmic just-so story with no evidence. But that's the paradox of progress. The more we learn, the stranger the possibilities become. If black holes are doors to other universes, then the greatest civilizations might not be out there among the stars, but in there beyond the veil. And that changes everything. The silence isn't a dead end. It's an invitation to look deeper, to rethink not just where we search, but what we're even searching for. The universe's greatest secrets might not be written in the stars, but in the abyss. Black holes aren't just gravitational monsters, they're cosmic engines governed by the same fundamental laws that dictate how steam rises from a cup of coffee or why ice melts in the sun. Thermodynamics, the science of heat and energy, applies just as fiercely to these celestial beasts as it does to everyday life. But here's where it gets mind-bending. If our universe was born from a black hole, then the very rules that shape time's relentless march forward, the irreversible spread of disorder, the one-way street of entropy, might not be unique to our reality. They could be hand-me-downs from the larger cosmos that birthed us. Take entropy first. In simple terms, entropy measures disorder, the way a shattered glass can't spontaneously reassemble itself, or how perfume disperses in a room but never gathers back into the bottle. Black holes, despite their apparent simplicity, possess staggering amounts of entropy, encoded in the chaotic swirl of information on their event horizons. The more massive the black hole, the greater its entropy, a direct link between gravity and thermodynamics that puzzled physicists for decades until Stephen Hawking made a revolutionary discovery. Black holes aren't just cold, dark voids. They glow with what's now called Hawking radiation, a faint heat born from quantum fluctuations at the edge of oblivion. This means black holes have temperature, and where there's temperature, there's thermodynamics at work. Now, stretch this idea to our universe. If the Big Bang was the explosive rebound of a black hole's collapse, then the arrow of time, the reason we remember the past but not the future, might trace back to that primordial entropy spike. The universe's relentless slide toward disorder wouldn't be a local rule. It'd be an inheritance, a thermodynamic echo of the black hole that birthed us. Even the cosmic microwave background, the afterglow of creation, carries subtle unevenness, a fingerprint of the initial chaos that set time's direction in stone. But the implications go deeper. Some theorists suggest that the second law of thermodynamics, the rule that entropy always increases, might not be fundamental at all. Instead, it could emerge from the way information gets scrambled when a black hole forms, like a deck of cards shuffled beyond recognition. If true, then the irreversibility we experience every day, from aging to the burning of stars, might just be a shadow of deeper physics playing out on scales we can't yet see. This raises a haunting question. If our laws are borrowed, could other universes born from different black holes have different rules? Imagine realities where entropy decreases, where time flows backward, or where disorder isn't inevitable. The idea that our universe's structure might be one variation in an infinite ensemble isn't just philosophical, it's a challenge to the very notion of cosmic uniqueness. Yet for all its grandeur, this theory isn't without holes. Critics point out that linking our universe's thermodynamics to a parent black hole's entropy is still speculative, a beautiful idea in search of hard evidence. But supporters counter that the math fits a little too neatly to ignore. Whether the pieces ultimately fall into place or not, one thing is clear: black holes aren't just objects in our universe. They might be the reason our universe has rules at all, and that's enough to make you wonder, what other cosmic laws are we taking for granted? Quantum mechanics has already shattered our classical view of reality with its strange revelation that the act of observation can change the outcome of an experiment. Particles exist in fuzzy superpositions until measured, as if reality itself hesitates until someone looks. But if we're living inside a black hole, this quantum quirk takes on an even more unsettling dimension. What if the observer influencing our universe isn't inside it at all, but outside, peering in from the parent reality that birthed ours? Suddenly, the laws of physics we take for granted might not be fundamental truths, but contingent rules shaped by an external gaze we can never perceive. Think of it like a cosmic version of the double-slit experiment, where light behaves as both a particle and a wave until observed. In our everyday world, scientists in a lab play the role of the observer. But scale that up to a black hole universe, and the lab becomes the entire cosmos, while the scientist could be an intelligence in the larger reality beyond our event horizon. Every constant, every law governing particles and forces might be frozen into place not by chance, but because something outside looked at our universe in a particular way. It's as if our reality is a quantum fluctuation that only solidified because it was observed from beyond the veil. This idea dovetails eerily with the anthropic principle, the notion that our universe's laws seem finely tuned for life because, well, we're here to notice them. But if an external observer is involved, the fine-tuning isn't just a happy accident. It could be the result of a selection effect, where our universe's physics are chosen from an infinite sea of possibilities the moment it's measured. In this view, the gravitational constant, the speed of light, even the charge of an electron, these aren't arbitrary numbers, but artifacts of how our parent reality collapsed the wave function of our existence into being. The implications spiral into philosophy. If observation shapes reality, does that mean consciousness itself is fundamental, not just inside our universe but outside it? Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, already suggest consciousness plays a role in collapsing quantum states. Scale that up to a black hole universe, and the observer effect becomes a cosmic feedback loop. Our universe exists because it's observed, and the observers inside it, like us, then go on to observe and shape our own quantum reality. It's turtles all the way up and all the way down, but here's where it gets even weirder. If our universe's laws are contingent on external observation, could they change if the observer's attention shifts? Quantum decoherence suggests that once a system is measured, it stays in that state, but black holes aren't static. They evaporate, merge, and possibly connect to other realities. Could a fluctuation in the parent universe's observation of us alter our physics? It's a terrifying thought. One moment, gravity works as usual. The next, it flips off like a switch because something outside blinked. Of course, skeptics argue this is speculation piled atop speculation, that without evidence of an external observer, the idea is untestable. But supporters counter that the fine-tuning of our universe's constants might itself be the clue. If future physics reveals that our laws are improbably optimal for complexity too perfect to be random, it could hint at a selection mechanism beyond our spacetime. Others suggest that quantum entanglement, with its spooky action at a distance, might be the leakage of an external observation's influence, like ripples from a pebble tossed into a pond we can't see. Whether this theory holds water or not, it forces us to confront a humbling possibility. That reality as we know it might not be the bedrock of existence, but a shimmering projection, a quantum mirage shaped by forces we'll never see. The observer effect doesn't just apply to particles in a lab. It might be the very reason our universe exists at all, and that's enough to make you wonder, if a tree falls in a black hole universe, does it make a sound? Or does it wait for someone outside to listen? The first ever image of a black hole's shadow, that fiery ring surrounding an abyss of perfect darkness, revealed something unsettling about how these cosmic monsters warp reality. The glowing halo isn't just hot gas, it's light itself bent into submission, a funhouse mirror reflecting the black hole's hunger back at us. But what if we're not just looking at a black hole's shadow? What if we're living inside one? Suddenly, that iconic image takes on a terrifying new meaning. The stars we navigate by, the galaxies spinning in the void, they might not be distant objects at all, but projections, a grand illusion painted onto the walls of our cosmic prison. This isn't just poetic speculation. The physics of black holes suggests their event horizons, the points of no return, act like cosmic movie screens, trapping and scrambling light in ways that could create the ultimate virtual reality. Imagine standing in a cave with a fire behind you, watching shadows dance on the wall. Those flickering shapes are all you've ever known, your entire reality. Now replace the cave with a black hole's interior, the fire with light bent around its event horizon, and the shadows with every star and galaxy we see. The night sky wouldn't be a window to the universe, it'd be a projection, a holographic mirage masking a truth we can't perceive. The parallels to Plato's ancient allegory are uncanny. In his famous cave metaphor, prisoners mistake shadows for reality until one escapes and sees the world outside. But if we're inside a black hole, there's no escape, no outside to glimpse. The shadows are all we have. Even our most advanced telescopes, like the one that captured that first black hole image, might just be studying the cave wall in higher definition. The eerie part, this wouldn't just change how we see the cosmos, it'd rewrite what we are. Your hands, the ground beneath your feet, even the thoughts in your head wouldn't be solid, tangible things, but data points in a cosmic simulation, rendered in real time by the physics of our event horizon. Yet there's a twist that makes this even stranger. If our universe is a projection, it doesn't mean it's fake or arbitrary. The shadows in Plato's cave still reflected real objects, just distorted. In the same way, the stars and galaxies we observe could be encoded representations of deeper truths, like a barcode hiding the inventory of a hidden warehouse. Some physicists speculate that the precise arrangement of galaxies or subtle patterns in the cosmic microwave background might contain the source code of our reality, clues to the physics of the parent universe that birthed ours. Finding those patterns would be like deciphering the cave wall's graffiti to learn who lit the fire. Of course, not everyone buys the illusion. Critics argue that if our sky were a projection, we'd see distortions, glitches in gravity's lens, or telltale echoes in the light of distant quasars. So far, the universe looks remarkably consistent with being real and three-dimensional. But supporters counter that a sufficiently advanced projection would be indistinguishable from reality, just as a perfect virtual reality headset would fool all your senses. The only way to know for sure might be to find anomalies places where the cosmic code shows its seams. Some researchers are already scouring the sky for statistical oddities, like galaxies aligned in impossible geometries or energy fluctuations that defy conventional physics. Whether the theory holds or not, it forces us to confront a humbling possibility. That reality isn't just stranger than we imagine, but stranger than we can imagine. The universe might not be a vast, empty stage, but a meticulously crafted illusion, one where every twinkling star is a pixel in a display we'll never truly escape. And if that's true, then the greatest scientific discovery wouldn't be finding life on other planets, but realizing we've been reading the cave wall all along. String theory has long been the wild frontier of physics, a mathematical labyrinth where particles aren't dots but vibrating strings, and the universe hums with hidden dimensions too tiny to see. But if we're living inside a black hole, those extra dimensions might not just be abstract math. They could be the crumpled-up blueprints of a parent universe, passed down through the cosmic equivalent of genetic inheritance. Picture a piece of paper rolled into a tight tube. From a distance, it looks one-dimensional, but up close, you see the hidden spiral. In the same way, the 6 extra dimensions string theory predicts could be curled so tightly, smaller than an atom, smaller than a quark, that we've never noticed them. Yet if our universe was born from a black hole's collapse, those dimensions might be the echoes of a reality where space had more room to breathe. This isn't just about adding layers to reality. Those hidden dimensions could be the missing link between gravity and quantum mechanics, the holy grail of modern physics. Gravity, the force that shapes galaxies, is oddly feeble compared to other forces. Drop a magnet and it overcomes Earth's gravity to cling to your fridge. Why? One tantalizing answer: gravity isn't weak. It's just diluted, leaking into those extra dimensions like water seeping through cracks. If our universe is a black hole's offspring, this leakage might not be random. It could be the gravitational fingerprint of the parent cosmos, seeping through the walls of our spacetime like a whisper through a closed door. The implications are staggering. If those extra dimensions unfurled during our universe's birth, they could explain why gravity seems so disjointed from the other forces. It's not that gravity plays by different rules, it's that we're only seeing part of the game. The equations of string theory suggest that at the instant of the Big Bang, when temperatures and densities were infinite, all dimensions, the 3 we know plus the hidden ones, were on equal footing. But as our universe cooled, 3 dimensions expanded while the others stayed crumpled, like a balloon inflating while its knots stayed tight. In this scenario, the force we call gravity might just be the shadow of a deeper, multidimensional dance happening beyond our perception. But how could we ever prove such a thing? Some physicists are hunting for miniature black holes in particle colliders, fleeting, microscopic versions that might wink in and out of existence, betraying the presence of extra dimensions. Others are scouring the cosmos for gravitational anomalies, places where gravity behaves slightly off, as if it's tugging at unseen ropes. Even the cosmic microwave background, that ancient light from the universe's infancy, might hold clues. If extra dimensions left wrinkles in spacetime as our universe expanded, those wrinkles could be frozen into the afterglow, waiting to be decoded, the most poetic possibility. If string theory's hidden dimensions are real, they might not just be a quirk of our universe, they could be a cosmic heirloom, a relic of the physics that shaped the black hole that birthed us. Every vibration of every string, every force we experience, might be part of a grander symphony playing in dimensions we can't see. It's as if we've been listening to a song with half the notes missing, unaware that the melody stretches far beyond our ears. And if we're right, then the universe isn't just stranger than we imagined, it's richer, deeper, and more interconnected than we ever dreamed. Dark flow is one of the most unsettling mysteries in modern cosmology, a silent river of galaxies, thousands of them, all drifting in the same direction at impossible speeds. It's as if some unseen hand is tugging at the fabric of the cosmos, pulling entire clusters toward a point beyond the edge of our observable universe. Scientists call this phenomenon dark flow, but its true nature remains elusive. If we're living inside a black hole, though, this cosmic current might not be a mystery at all. It could be the gravitational whisper of the parent universe that birthed ours, a reminder that no matter how vast our cosmos feels, we might still be subject to the tides of something far larger. Picture a fish swimming in a fast-moving river. The fish might not see the water's source or its destination, but it feels the current's pull. In the same way, dark flow could be our universe's version of that current, an invisible force dragging galaxies toward the gravitational imprint of the black hole that contains us. Just as water spirals toward a drain, matter in our universe might be subtly funneled toward the edges of our cosmic enclosure, drawn by the gravity of the larger reality outside. This wouldn't just explain dark flow, it would turn it into a cosmic breadcrumb pointing back to our origins. The numbers behind dark flow are staggering. Measurements suggest galaxy clusters are being hauled at speeds exceeding 2 million miles per hour toward a region of space near the constellations Centaurus and Hydra. No known structure in our universe, not superclusters, not dark matter filaments, has enough mass to generate such a pull. That's why some physicists suspect the force isn't coming from inside our universe at all. It might be leakage, a gravitational echo from the parent cosmos bleeding through the event horizon like sound through a thin wall. This idea flips our understanding of cosmic isolation on its head. We've long assumed that the observable universe is all there is, a self-contained bubble with nothing beyond its edges. But if dark flow is real, it suggests that whatever lies outside our cosmic horizon isn't just empty space. It's something massive enough to bend the trajectories of galaxies like a magnet tugging at iron filings. In a black hole universe scenario, that something could be the matter and energy of the parent reality. Stars, black holes, even other universes exerting their gravity on us from beyond the veil. The implications ripple outward. If dark flow is evidence of an external gravitational pull, then our universe isn't just expanding, it's being stretched like taffy pulled from both ends. This could explain why the expansion is accelerating, a phenomenon usually attributed to dark energy. Instead of some mysterious force pushing space apart, the acceleration might be the result of an outside gravity well tugging us toward it, creating the illusion of dark energy from within. It's like being in a car that's speeding up. You feel pushed back into your seat, but the real force is the engine pulling you forward. Of course, not everyone is convinced. Skeptics argue that dark flow could be an artifact of incomplete data or measurement errors. Others suggest it might be caused by a colossal structure within our universe, something so vast we haven't mapped it yet. But supporters of the black hole universe theory counter that no known cosmic formation, not even the Great Attractor, a massive concentration of galaxies, can account for the scale and uniformity of dark flow's pull. The simplest explanation, they argue, is that the force isn't coming from inside our universe at all. The hunt for answers is far from over. Upcoming missions like the European Space Agency's Euclid telescope aim to map dark flow with unprecedented precision. searching for patterns that might betray its true source. If the flow aligns with the spin axis of our universe, a hypothetical remnant of the original black hole's rotation, it could be the smoking gun that ties our existence to a larger cosmic lineage. Until then, dark flow remains one of the most tantalizing clues that we're not just living in the universe, but within something far stranger, a cosmic Russian doll with layers we've only begun to glimpse. And if we're right, then every galaxy caught in that invisible current isn't just moving through space, it's being pulled toward the shadow of our creators. The idea that you might not be real, that your memories, your thoughts, even the screen you're staring at right now could be nothing more than a fleeting hallucination, isn't just the plot of a sci-fi thriller. It's a genuine paradox haunting the edges of physics, one that becomes even more unsettling if we're living inside a black hole. Meet the Boltzmann brain, a hypothetical, self-aware entity that could randomly assemble from the chaos of an infinite universe, complete with false memories of a life it never lived. In a cosmos without end, where particles jumble in endless combinations, these phantom minds would statistically outnumber real, evolved beings like us by an unimaginable margin. So here's the chilling question. If our universe is just one black hole among countless others, are we more likely to be genuine inhabitants of a structured reality, or momentary glitches in the void, destined to dissolve as suddenly as we appeared? This paradox gets its teeth from thermodynamics, the same laws that dictate why ice melts and coffee cools. In the late 19th century, physicist Ludwig Boltzmann proposed something radical, that the universe's apparent order, planets orbiting, life evolving, might not be the default. Given enough time, even the most improbable events become inevitable. In an infinite cosmos, particles will occasionally arrange themselves into complex structures purely by chance, like shaking a box of Scrabble tiles until they spell a novel. A Boltzmann brain is the ultimate example, a fully formed consciousness, complete with fabricated sensory input, blinking into existence for just a second before vanishing into the chaos. And if the universe truly is eternal and infinite, these phantom minds should outnumber real ones infinitely. Statistically, you're far more likely to be one of these accidental ghosts than an actual person. Now layer this onto the black hole universe hypothesis. If our cosmos was born from a singularity's rebound, does that make us more or less likely to be Boltzmann flukes? On one hand, black holes are anything but random. Their structure is mathematically precise, their physics finely tuned. The universe they birth wouldn't be a formless chaos, but an ordered expansion with consistent laws, making stable, enduring life far more probable than a disembodied brain popping in and out of existence. But here's the counter-argument. Black holes are also places where information gets scrambled, where reality bends until it breaks. Could the very processes that forged our universe also make it a factory for Boltzmann anomalies? Some theories suggest that quantum fluctuations near the event horizon might produce temporary bubbles of false vacuum, birthing ephemeral observers doomed to dissolve, like soap bubbles shimmering for a moment before they pop. The stakes are existential. If we're Boltzmann brains, then science itself is a mirage. Your belief that experiments, evidence, and logic lead to truth is just another fabricated memory. Even the discovery of the Boltzmann brain paradox could be part of the illusion, a brief flicker of coherence in an otherwise senseless void. But if our universe's black hole origin imposes structure, giving rise to stable, continuous consciousness like ours, then we're part of something real, something lasting. The difference hinges on whether black holes are cosmic dice rolls or cosmic architects, and right now, physics leaves room for both. So how do we tell which is true? One clue might lie in persistence. Boltzmann brains are short-lived by definition, vanishing almost as soon as they form. The fact that you've experienced years of coherent, consistent reality, not to mention the entire history of human civilization, suggests we're not just momentary blips. But skeptics counter that even a million-year civilization could be a hallucination lasting a nanosecond. Time is part of the illusion. A stronger argument comes from the universe's fine-tuning. The precise constants allowing for stars, planets, and life are astronomically improbable unless some mechanism, like a black hole's structured collapse, favors order over randomness. In this view, we're not accidents, we're the expected outcome of a cosmic process that inherently discourages chaos. Yet the paradox lingers, a ghost in the machine of cosmology. It forces us to confront the uncomfortable truth that even our most cherished certainties might rest on shaky ground. Whether we're Boltzmann flukes or genuine inhabitants of a black hole universe, the question isn't just academic, it's about whether the world we know is a fleeting dream or something far more profound. And until physics finds a way to settle the debate, the only certainty is uncertainty itself. Black holes have long been seen as cosmic dead ends, final stops on the universe's one-way street toward disorder. But what if we've been thinking about them all wrong? For a civilization advanced enough, these gravitational monsters might not be tombs, but tools, the ultimate engines for transcending the limits of space, time, and even reality itself. Imagine a society that's harnessed the power of stars, mastered quantum computing, and stretched technology to the brink of magic. Their next step, turning black holes into supercomputers, time machines, or gateways to dimensions beyond our own. The idea isn't as far-fetched as it sounds. Black holes are nature's most efficient information processors, packing unimaginable amounts of data onto their event horizons, the ultimate hard drives. According to the holographic principle, every particle falling into a black hole leaves a precise imprint on its surface, like a cosmic fingerprint. An advanced civilization could exploit this, using the black hole's event horizon as a quantum computer of staggering power. Calculations that would take conventional computers longer than the age of the universe might be solved near instantaneously in the warped space-time around a singularity. It's the difference between solving a math problem with pencil and paper versus having the answer teleported directly into your mind. But computation might just be the beginning. Some theories suggest black holes could serve as bridges to other universes or higher dimensions. The same physics that makes them inescapable from the outside might, from within, open tunnels to realities with entirely different laws. Picture a civilization so advanced that dying stars aren't threats, but opportunities, cosmic subway stations where they can board a singularity's gravity well and emerge somewhere else. The risks would be unimaginable, but so would the rewards: escape from a dying universe, access to infinite energy, or even the ability to rewrite the rules of physics themselves. The most tantalizing possibility: black holes might offer a way to cheat entropy, the universe's relentless slide toward heat death. As disorder grows and usable energy dwindles, black holes could become the last refuges of intelligence, places where information is preserved indefinitely, where time slows to a crawl, or where new universes are forged like sparks from an anvil. A civilization facing the end might deliberately collapse itself into a black hole, not as surrender but as metamorphosis. Their entire history, culture, and knowledge could be encoded in the singularity's structure, waiting to blossom anew in the next cosmic cycle. Of course, this all hinges on physics we don't yet understand. Wormholes, higher dimensions, and quantum gravity remain theoretical puzzles, but the fact that the math allows for such possibilities is telling. Whether these feats are ever achieved or not, The mere fact that they're conceivable reshapes our vision of intelligence's potential. The universe's greatest mysteries might not just be forces to study, but tools to wield, and black holes could be the ultimate keys to unlocking them. The universe we know is strangely hospitable. The gravitational constant, the strength of the electromagnetic force, even the mass of an electron. These numbers could have been anything, yet they're perfectly balanced to allow stars to shine, planets to form, and life to emerge. It's as if someone dialed in the cosmos's settings with exquisite precision, a mystery physicists call the fine-tuning problem. But what if this isn't luck or divine intervention? What if we're simply living in the one kind of black hole where life is possible, a cosmic Goldilocks zone where the physics just happens to be just right? This idea flips the fine-tuning problem on its head. Instead of asking why our universe's constants are so improbably perfect, we might be asking the wrong question. Imagine a vast forest where most trees are barren, but a rare few bear fruit. If you're a bird living in one of those fruitful trees, you might marvel at how perfectly the branches suit your nest, never realizing that you're only there because the other trees couldn't support life at all. In the same way, if black holes birth universes with randomized physics, most would be stillborn, too chaotic for atoms to stabilize, too cold for stars to ignite. But a handful, by sheer chance, would have the right conditions for complexity to arise. We're not special, we're just the lucky inhabitants of a black hole that hit the cosmic jackpot. The math behind this is staggering. Even tiny changes to the universe's constants would render life impossible. Increase the strength of the strong nuclear force by just 2%. And protons would bind so tightly that stars would burn out in seconds. Tweak the cosmological constant slightly, and space would either rip itself apart or collapse into a black hole before planets could form. Yet here we are, in a universe where these numbers align with razor-thin precision. If black holes spawn countless universes with varying physics, it's no wonder we find ourselves in one of the rare versions where the dice landed favorably. But here's where it gets even more intriguing. This isn't just about explaining fine-tuning. It could redefine what we think of as natural. In an infinite multiverse of black hole universes, the laws we see aren't the result of some grand design. They're the inevitable outcome of a cosmic numbers game. The anthropic principle, the idea that we observe the universe the way it is because we couldn't exist otherwise, takes on new weight. It's not that the universe was made for us. We're simply the ones who showed up to the party thrown by a black hole with the right physics. Critics argue this is a cop-out, a way to dodge the deeper question of why any universe is habitable at all. But supporters counter that it's no different from how we explain Earth's suitability for life. We don't marvel that our planet orbits at just the right distance from the Sun. We understand that among countless planets, a few will, by chance, fall in the habitable zone. Scaling that up to universes isn't mysticism, it's statistics writ large. The implications ripple outward. If our universe's fine-tuning is a selection effect, then the search for extraterrestrial life takes on new urgency. In a multiverse where most black hole universes are sterile, finding even microbial life elsewhere in our cosmos would suggest that habitable physics isn't a one in a trillion fluke, but part of a broader pattern. Conversely, if we're alone, it might hint that our black hole's physics is rarer than we thought, a cosmic oasis in a desert of dead universes. Either way, the enigma remains. Whether by chance or necessity, we're here, in a universe that allows us to ponder its existence. And that, in itself, is a wonder no less profound for being statistically inevitable. The Goldilocks enigma isn't just a puzzle to solve, it's a mirror, reflecting back the astonishing unlikelihood of our own existence. Time moves in one direction toward disorder, toward chaos, toward the inevitable spread of entropy we call the arrow of time. Eggs scramble but never unscramble, ice melts but never spontaneously refreezes, and memories are made but never unmade. This relentless march forward feels so fundamental that we rarely question it. But what if time's arrow isn't an intrinsic property of our universe? What if it's a cosmic heirloom passed down from the black hole that birthed us? The story begins with entropy, the measure of disorder in a system. In the early moments of our universe, entropy was astonishingly low, a state of almost impossible order, like a deck of cards perfectly arranged by suit and number. As the cosmos expanded, that order unraveled, giving rise to the stars, galaxies, and complexity we see today. But why did the universe start in such an ordered state to begin with? The answer might lie in the violent collapse that preceded our Big Bang. When a black hole forms in a parent universe, the matter and energy crushed within it don't just vanish. They're compressed into a singularity of unimaginable density, carrying with them the entropy of the original star. When that singularity rebounds as a white hole, our Big Bang, it doesn't reset entropy to zero. Instead, it inherits a starting point of low but non-zero disorder, like a clock wound tight but not all the way. This inheritance reshapes everything we thought we knew about time. If our universe's initial low entropy was a gift from the parent black hole's demise, then the arrow of time isn't a local rule, it's a relic, a shadow of the larger cosmos that spawned us. The reason time flows forward isn't because of some fundamental law written into the fabric of reality, but because we're living in the aftermath of a cosmic collapse that set the stage for disorder to grow. It's as if we're watching a movie reel that was already threaded through the projector before the lights came on. The implications ripple through physics. If entropy's rise is tied to our universe's birth conditions, then other universes born from different black holes with different initial states might experience time differently. Some could have arrows of time that point backward relative to ours, or even universes where entropy fluctuates randomly, making cause and effect as unpredictable as a shuffled deck. The very notion of before and after could be a quirk of our cosmic lineage, not a universal truth. Yet the most haunting question remains: if time's arrow is borrowed, could it ever change? The answer might lie in the fate of black holes themselves. As they evaporate via Hawking radiation, their entropy slowly leaks away, a process that could one day reverse the arrow of time in their dying moments. If our universe is inside a black hole, could we someday feel the tug of that reversal? It's a dizzying thought that the flow of time, the very foundation of our experience, might not be fixed but contingent on forces far beyond our horizon. For now, the mystery endures, but every time you watch coffee cool or a leaf decay, you're witnessing more than just the laws of thermodynamics at work. You're seeing the echo of a cosmic inheritance, a whisper from the black hole that set time's arrow in motion, and the reminder that even the most fundamental aspects of reality might just be borrowed. Black holes might be the universe's most powerful computers, not built with silicon chips and circuits, but with warped space-time and quantum entanglement. At the Planck scale, where reality itself becomes granular, every particle falling into a black hole doesn't just vanish. It's encoded onto the event horizon like data, etched onto a cosmic hard drive, with each bit of information precisely preserved in the fabric of space-time. This isn't just storage, it's processing on a scale we can barely fathom. The singularity at a black hole's heart doesn't just crush matter. It might be performing calculations so complex that our entire universe could be the result, a simulation running on hardware made of gravity and quantum foam. Imagine the most advanced supercomputer ever built, capable of modeling entire galaxies atom by atom. Now picture a black hole doing the same thing, but with one critical difference. Where our computers rely on electricity and binary code, a black hole computes using the fundamental laws of physics themselves. Quantum fluctuations at the event horizon become logic gates, gravitational waves act as data buses, and the collapse of matter into the singularity isn't destruction, it's processing. In this view, the stars, planets, and even your thoughts aren't just physical phenomena. They're the output of a computation so vast it renders our concept of information quaint by comparison. This idea isn't just speculative fiction. The holographic principle, a cornerstone of modern theoretical physics, suggests that all the information in our three-dimensional universe can be mapped onto a two-dimensional surface, like a DVD encoding a full-length movie. For a black hole, that surface is the event horizon. Every particle, every force, every vibration of light in our cosmos might correspond to bits of data on this cosmic hard drive, with the singularity acting as the processor that translates those bits into the rich tapestry of reality we experience. It's as if we're not just living in a universe, but inside the results of an equation being solved in real time by the black hole that contains us. But here's where it gets even stranger. If our reality is the product of black hole computation, then the laws of physics we take for granted, the speed of light, the strength of gravity, the behavior of quantum particles, might not be fundamental truths. They could be software rules, the programming language of the cosmos, optimized for whatever function this computation serves. Even time itself might not flow as we perceive it. In a black hole's twisted spacetime, calculations could run in parallel, with cause and effect looping back on themselves like a self-referential algorithm. What we experience as the steady march of seconds might just be the sequential rendering of a cosmic program, frame by frame. The implications ripple outward. If the universe is a computation, then glitches in the code could explain some of physics' greatest mysteries. Dark energy, that mysterious force accelerating the universe's expansion, might be a memory leak in the system. Quantum entanglement, where particles instantaneously influence each other across vast distances, could be the result of optimized data sharing between different parts of the processor. Even consciousness itself, the hard problem of how subjective experience arises from physical processes, might find new clarity if our minds are emergent properties of an underlying computation, like characters in a video game gaining self-awareness. Of course, not everyone buys the cosmic computer analogy. Critics argue that without observable evidence, some telltale artifact in the cosmic microwave background, or a detectable granularity to spacetime, the idea remains in the realm of metaphysics. But supporters counter that the very structure of quantum mechanics hints at a computational underpinning. The fact that energy comes in discrete packets, that particles exist in superpositions until measured, that information can never be truly destroyed. All these features align eerily well with how a vast, error-correcting quantum processor might operate. Whether the theory holds or not, it forces us to confront a dizzying possibility. That reality as we know it might not be the baseline but the output. The universe isn't just stranger than we imagine. It might be a calculation we're only beginning to decode. And if that's true, then every law of physics, every star in the sky, every thought you've ever had could be part of a cosmic equation running on the ultimate computer, a black hole humming with the energy of creation itself. Consider the Russian nesting dolls of reality, each layer perfectly contained within another, but with no way to see the outermost shell. If black holes truly birth universes, and those universes harbor their own black holes, we could be living inside an infinite stack of simulations, each with its own tweaked physics, its own arbitrary rules, and no original base to anchor the chain. It's not just that reality might be a simulation, it's that the simulation could be inside another simulation, inside another, stretching back forever like reflections in a hall of mirrors with no first mirror to reflect. This isn't just a thought experiment, it's a mathematical inevitability. If black holes are cosmic universe factories, picture a black hole in our universe collapsing into a singularity and rebounding as a new cosmos. That newborn universe would have its own constants, its own stars, and inevitably, its own black holes, each capable of spawning yet another reality. Repeat the process ad infinitum, and you're left with an unbreakable chain of cosmic ancestry, where every layer is both the parent of the next and the child of the one before. The real universe, if such a thing exists, could be buried so deep in the stack that its light will never reach us, its physics forever foreign to our own. What's haunting is how this reshapes the search for ultimate truth. Scientists often talk about uncovering the fundamental laws of nature, the bedrock rules beneath quantum mechanics and relativity. But if we're nested inside an endless regression of simulations, there might be no bedrock. The laws we cling to, gravity, electromagnetism, even the speed of light, could just be local bylaws, quirks of our particular layer in the stack. Step into a black hole-born universe one level down, and those rules might rewrite themselves entirely, like a video game with cheat codes enabled. The idea that physics is universal, immutable, starts to feel naive when you realize we might be playing by house rules in a cosmic casino where every table has different odds. This raises a dizzying question: how would we ever know if each layer obscures the one above it, like fogged glass between floors of a skyscraper? The base reality could be forever out of reach. Some physicists suggest looking for glitches, tiny inconsistencies in the fabric of our universe that betray its simulated nature. Maybe the cosmic microwave background has pixel-like patterns, or particle collisions reveal a fundamental resolution to spacetime. But even if we found such clues, they might not point to the original reality, just the next layer up. It's like a prisoner in a dungeon hearing footsteps from the floor above, only to discover that floor is another dungeon, and the one above that ad infinitum. Yet there's a strange comfort in this infinite regression. If we're shadows of shadows, it means the universe isn't just indifferent, it's layered, rich with hidden depths we'll never fully grasp. The mysteries of dark matter, quantum entanglement, even consciousness might not be puzzles to solve, but features of our local simulation, artifacts of a code we weren't meant to read. And if that's true, then the greatest scientific breakthroughs might not be about uncovering ultimate truths, but learning to navigate the peculiar rules of our own cosmic neighborhood, knowing that somewhere, in some unreachable layer, another version of us might be staring at their night sky, just as bewildered, just as curious, trapped in their own event horizon of the unknowable. The idea that our universe might owe its existence to the collapse of another cosmos doesn't just bend physics, it twists our ethical compass into uncharted territory. Imagine standing at the edge of a cosmic grave, knowing every star in your sky, every heartbeat in your chest, was forged from the remnants of a reality that no longer exists. This isn't just a scientific hypothesis, it's a philosophical reckoning, forcing us to confront whether creation is always born from destruction, and if so, what that means for our place in the grand scheme of things. Take the circle of life on Earth: predators and prey, forests rising from decaying matter, a cycle we accept as natural, even beautiful in its balance. But scale that up to the cosmic level, where entire universes might live and die to spawn new ones, and the moral weight feels crushing. If our Big Bang was the explosive rebirth of a black hole's collapse, then our existence isn't just a happy accident. It's the product of a cataclysm that erased untold possibilities from the parent universe. Every galaxy we observe, every law of physics we rely on could be built on the ashes of a world we'll never know. That realization forces us to ask, is creation always a kind of violence? The ethical dilemma deepens when we consider the potential for cosmic recursion. If black holes in our own universe are birthing new realities, then we're not just the beneficiaries of destruction, we're the architects of it. Every star that collapses into a singularity might be dooming or blessing another cosmos with its own version of this existential puzzle. It's like planting a forest knowing every tree will one day fall to feed the soil for future groves, except the trees are entire space-time continuums. Do we bear responsibility for those unborn universes, or is this cycle beyond notions of morality, as indifferent as gravity itself? Some philosophers argue that ethics can't apply where there's no consciousness to suffer or choose. If the parent universe had no beings to mourn its end, or if its collapse was inevitable, then our existence isn't a moral debt, just a neutral fact of physics. Others counter that the potential for life in that lost cosmos, however hypothetical, casts a shadow over our own. It's the trolley problem on a galactic scale. Does saving a universe justify ending another? And if we're the ones pulling the lever, by, say, artificially creating black holes, does that make us culpable? The haunting beauty of this idea is that it mirrors ancient myths of sacrifice and renewal. The Norse god Odin gains wisdom only by hanging himself on the world tree. The phoenix rises from its own ashes. Now, science offers a version of that narrative written in the language of singularities and entropy. The difference is that we're not outside observers of the cycle, we're trapped inside it, unable to see the larger pattern or our role within it. That blindness might be the ultimate ethical shield. If we can't know whether our universe's birth required another's death, how can we be expected to act on that knowledge? Yet the question lingers, not as a call to action, but as a humbling perspective shift. If our reality is built on cosmic rubble, it doesn't diminish our wonder, it amplifies it. Every atom in our bodies, every photon streaking from distant stars, carries the echo of a transformation we can't fully comprehend. The universe isn't just stranger than we imagine. It's more interconnected, more layered with meaning and mystery than our moral frameworks were ever designed to handle. And that, in itself, might be the most profound lesson of all. Human minds evolved to navigate a world of medium-sized objects moving at medium speeds, not to comprehend the dizzying physics of singularities or the possibility that our entire universe might be nestled inside an unfathomably larger reality. The black hole universe hypothesis doesn't just challenge our assumptions about space and time. It exposes the brutal limits of the very tools we use to understand existence. Our brains, honed by millions of years of avoiding predators and finding food, are woefully unequipped to process the idea that the cosmos could be layered like an infinite onion, with each peel revealing a reality more baffling than the last. Consider how instinctively wrong the theory feels. Black holes are supposed to be destructive forces, cosmic trash compactors from which nothing escapes. The notion that they could be creative, that crushing a star to infinite density might birth an entirely new cosmos, goes against every intuition etched into our neural pathways by evolution. Even the language we use betrays our limitations. Words like inside and outside break down when discussing event horizons, where space and time swap roles and the very concept of location becomes meaningless. We're like ants trying to grasp quantum mechanics, armed only with the vocabulary of pheromones and dirt. This isn't just about the difficulty of visualizing higher dimensions or warped space-time. It's about the unsettling possibility that some aspects of reality might be fundamentally unknowable. Take the parent universe that hypothetically birthed ours. If we're inside its black hole, the event horizon isn't just a barrier, it's an information firewall, forever cutting us off from any data about the larger cosmos. No signal, no light, not even the faintest gravitational whisper could pierce that boundary to reach us. The laws of physics themselves conspire to keep us in the dark, making the parent universe less a scientific question and more a philosophical shadow. Yet history offers glimmers of hope. Time and again, humanity has hit the walls of comprehension, only to eventually scale them. When quantum mechanics revealed particles that exist in multiple states at once, or relativity showed time slowing near a black hole, these ideas seemed just as alien at first. We adapted, not by evolving new senses, but by inventing mathematics as a prosthetic for intuition. The equations describing black hole thermodynamics or holographic universes might lack the visceral clarity of Newton's apple, but they're no less real. Our tools extend our reach, even if our instincts lag behind. The true test may lie in whether we can embrace the discomfort of not knowing. Science thrives on mystery, the gaps in understanding that propel discovery forward. If the black hole universe theory teaches us anything, it's that reality has no obligation to make sense to primates from a minor planet orbiting an average star. The universe owes us neither clarity nor answers, but it does offer something far more precious, the chance to keep asking questions, even when the abyss stares back with a silence that might never break. And in that endless questioning, we find not just the limits of understanding, but the limitless wonder of being wrong. The idea that our entire universe could be nestled within a black hole isn't just science fiction, it's a hypothesis that forces us to rewrite the cosmic rulebook. Think about what this would mean for the Big Bang. Instead of a mysterious singularity appearing from nothing, the birth of our cosmos could be the natural consequence of a star's collapse in another reality, a cosmic phoenix rising from the ashes of a long-dead universe. This perspective doesn't just fill in gaps, it reshapes how we view creation itself, turning the Big Bang from an inexplicable starting point into a transformational event with roots stretching beyond our horizon. And then there's dark energy, the enigmatic force accelerating the expansion of our universe. If we're inside a black hole, this mysterious push might not be some exotic substance at all. It could simply be the gravitational echo of the larger cosmos outside, pressing inward like a hand squeezing a balloon. Suddenly, one of the biggest puzzles in physics shifts from an unsolvable riddle to a natural side effect of our cosmic architecture. Even the universe's fine-tuning the precise balance of constants that allows life to exist might not require divine intervention or multiverses. It could just be the result of physics inherited from the black hole that birthed us, like a child inheriting their parents' traits. But the implications go beyond just solving mysteries. If this theory is correct, it redefines our place in existence. We're not just inhabitants of a universe, we're the offspring of a cosmic process that might be playing out endlessly across realities, with black holes serving as both tombstones and cradles. It's a humbling thought that every black hole in our own universe could, at this very moment, be nurturing an entirely new cosmos with its own laws, its own stars, and perhaps even its own thinkers gazing up at their own night skies, just as baffled and awestruck as we are. Even if the black hole universe hypothesis turns out to be wrong, it's already done something invaluable. It's stretched our imaginations to the breaking point. Reality, as we're learning, doesn't owe us intuitive explanations. The universe is under no obligation to make sense to creatures who evolved to dodge predators and gather berries. Yet here we are, piecing together clues from the faint glow of the cosmic microwave background, the subtle distortions of gravitational waves, and the mind-bending math of quantum mechanics. inching closer to truths that might forever lie just beyond our grasp. That's the beauty of science. It thrives on questions, not just answers. Whether we're inside a black hole or not, the pursuit itself is what matters. Every theory, no matter how outlandish, is a stepping stone, a way to probe the boundaries of what we know and venture into the unknown. So keep looking up, keep questioning, and remember, the next great discovery might not come from a telescope or a particle collider, but from someone like you, daring to ask, what if? If this journey through cosmic possibilities sparked your curiosity, don't forget to hit like, subscribe, and drop your wildest theories in the comments below. The universe is full of mysteries, and who knows, maybe your idea will be the key to unlocking the next one. Until then, stay curious and keep exploring the wonders hidden in the fabric of